I build software for computers that don't exist yet. Imagine explaining that to your mother. I am Soham, and I work at QCware. We're a quantum algorithms company. In 10 to 20 years, quantum computing will become incredibly, incredibly powerful. And I'm going to show you some of the avenues that we're taking to use the power of quantum computing to improve machine learning. So, some of the first experiments in quantum computing were done by scientists that were trying to create the smallest bit of information. Right now, we use flash memory, and flash memory can get down to around 0.3 microns in size, which is about the size of a small bacteria. But what if you could go further? Can you store a bit of information in something as small as an electron? Well, an electron has a few energy levels, and here we'll focus on two of them here. The upper energy level and the lower energy level. One way you can store a bit is to say that if the electron is in the upper energy level, then it's a 1. And if the electron is in the lower energy level, it's a 0. Now, this is a totally valid way of storing a bit of information. You can retrieve if the electron is in 1 or 0 using lasers, and you can even flip between them to do real computation. So this is all well and good. But it turns out that at this scale, you can do more. And that's because at this scale, things act quantumly. They act very differently. We'll call a bit that acts differently in this way, in this quantum way, a qubit. Now, a qubit can exist in 1 or 0, but it can also exist in some part 1 and some part 0. So it's hard to understand what that means, and don't worry, Richard Feynman famously once said, he can surely say that nobody understands quantum mechanics. But while we don't understand it, we can write it down. So here's what a single bit, qubit, looks like. You can write it down as A part 0 plus B part 1. Those little lines around the 0 and 1, they are bracket notation. That's what we call bracket notation, and it just signifies state. What you need to know is that it's A part 0 and B part 1. And you can set A and B to almost anything that you want. They can be positive, they can be negative, they can even be complex, which leads to very powerful quantum interference effects. The only constraints on these A and B are that when you square them and then add them together, they make 1. But so you've gone and tried to store a single bit of information, but now you can store two whole complex numbers, A and B. That is crazy. That's like buying a black and white printer, but figuring out that it can print in color. I mean, truly astounding. Now, when you go to 2 qubits, it gets even crazier, because now you would have expected to have been able to store 2 bits of information, meaning one of 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. But now that it's quantum, it can exist in some part of each of these 4 states at once. So now you have 4 complex numbers. In general, when you have n qubits, you get 2 to the n coefficients. Now it's clear that if you have 2 to the n coefficients and just n qubits, you'd probably want to compute with the coefficients and not the qubits. So quantum computing brings the focus away from the bits of information and towards these coefficients. When you hit 500 qubits, you can now store more coefficients than there are atoms in the known universe times the number of atoms in the known universe. We like talking about the universe at this conference. That is astronomical. But of course, there are tons of caveats, and these are big caveats. First off, we can't write data to this quantum state efficiently. If you want to fill in all of those A's and B's and C's with whatever you want, that's exponentially many A's, B's, and C's. So it'll take exponential time. You can't do that. And reading data also. Every time you look at these electrons, you won't get information about the A's, B's, and C's. They'll snap to 1 or 0. And the only indication of what the A's, B's, and C's were are the probabilities of getting 1 or 0. Okay, so you can only pull a tiny bit of information out. And that is the beauty and the challenge of quantum algorithms, is to give the quantum computer a tiny bit of information, let it use internally all of this exponential state, and then when you get it out, you have to make sure that whatever you get out is useful. Now, 40 years ago, it was unknown whether this kind of computation was useful at all. But then in 1981, Richard Feynman showed that if you want to compute, if you want to simulate quantum mechanics, you need to use a quantum computer. You need to use a computer that works on the laws of quantum mechanics. Now that's pretty intuitive. If you want to simulate quantum mechanics, you need quantum mechanics. But then he posed a question, which is, are there any other problems in the world, not quantum mechanical in nature, that you can do better on a quantum computer? In 1994, Peter Shor showed us that that was the case. He showed us that if you have a full-scale quantum computer, you can factor large numbers efficiently. That means if I give you a gigantic number and I ask you to figure out what two numbers multiply to get it, that could take millions of years for a regular computer to do. But for a quantum computer, it could take just minutes. That started the field of quantum algorithms that showed us that quantum computing has power. And since then, there have been plenty of other algorithms proposed for various different tasks, including machine learning, chemistry. And fast forward to today, and we're really trying to build a quantum computer. There are billions of dollars of investment from governments. There are large companies like Amazon, Microsoft, IBM, Google that are all getting involved. And there are over 180 plus startups working on this. So now we're at the state of the industry where I can finally show you what a full quantum application can look like from the ground up. We'll start with the hardware. These are the people building the quantum computers. Some of them do it like I showed you before, like IonQ. They store the qubit in the outermost electron of some levitating ions. But there are many other ways of doing this. Tons of different architectures. Some of them are faster. Some of them can store more qubits. Some of them, they can create 3D grids that can play Super Mario. This is physics at its finest. But most of them are extremely big. And because they're big, it's not likely that in the near term they'll be on premises. They'll probably be vended out by the cloud. That's where services like Amazon Bracket come in. Amazon Bracket, you can hop on right now and experiment with some of those tiny quantum computers that people are building today. And it also gives some training and a unified interface to make it easy. On top of that, we have the application stack. This is the quantum software. That's where QCware focuses. We build custom quantum applications and algorithms for machine learning, optimization, chemistry. This here is a paper that we published alongside Boehringer Ingelheim showing that we can do drug development faster on a quantum computer. And that's the kind of thing that we do. And finally, at the very top, you have the end users. These are companies and organizations that have hard problems and are looking for quantum computing to solve them. These are some of the companies that we work with. You can see representatives from pharma, from energy, from finance, transportation, manufacturing. All of these companies are investing today because they don't want to fall behind like so many companies did with machine learning. So in this talk, first, I'll teach you some jargon. We use a lot of jargon in the industry. There are 3 terms that I think you should know. Then I'll show you 4 quantum algorithms for machine learning. One for neural networks, another for determinant sampling, which will help you select diverse representatives from a set, topological data analysis, which will help you understand the shape of your data, and compound matrices, which will take you from looking at pairwise interactions to group-wise interactions. And finally, I'll close off with some quantum algorithms trends and takeaways that you can use today. OK, for the jargon. First is classical. I've probably used this a lot. It means normal computation. Everything that we use today, ones and zeros, CPUs, GPUs. And I'm not picking on classical computation at all. In fact, it's the big dog in the park. It's the incumbent. It's not going to be surpassed by quantum computing anytime in the near future for most tasks. And that's because those tasks just don't need the exponential power of a quantum computer. Things like running PowerPoint, simple computations, classical computers will remain faster, maybe forever. But for certain problems, classical computers don't cut it. They look like this, where on the y-axis we have time to solution, and on the x-axis we have problem size. And past a certain problem size, Classical computers, they blow up. They may take years to solve that problem. And for these kinds of problems, we're looking to find quantum algorithms that don't blow up. We are right here in the industry. That's because we can't fit large problem sizes into quantum computers yet. But we're moving to the right. And when we cross over, when a quantum computer crosses over with the classical computer and can do something faster, something useful faster, that is called quantum advantage. This is payday for quantum computing companies. But it may come at different times for different industries. For example, it might be more useful to say quantum advantage for blank, for chemistry, for machine learning, for optimization. We think, the way it looks right now, chemistry is going to be the nearest term application for quantum computers. We're hoping to achieve quantum advantage for chemistry in the next 3 to 10 years for some very specific molecules. Quantum machine learning, optimization, Monte Carlo methods, differential equations, these we think are a little further out, but it gives us time to start understanding how these algorithms will help us. And the last term is near term. This is the kind of computer that we'll be dealing with in the next 3 to 10 years. We expect to have 100 to 1,000 qubits, but that won't be the main limitation. The main limitation is actually how noisy the computer is, which will stop us from running large circuits. Okay, let me explain circuits real quick. This is a quantum circuit. The horizontal lines represent qubits, and the big X at the top, that one box, that represents an operation on a single qubit. And then the vertical lines, they represent 2-qubit operations that touch 2 qubits. We call them 2-qubit gates. In particular, this is called the fermionic beam splitter gate. So that gives you an understanding of maybe what a quantum circuit looks like. It's not an epic Guitar Hero riff, but it's something we use all the time. So now I'll explain noise. If I want to load an image onto a quantum computer, I can do this a few different ways. I can run a circuit that's very naive, that looks like this. That's just a diagonal line of 2-qubit gates, and it doesn't use the resources efficiently. So clearly, you can see what we get out is pretty garbage. But if you can design effective, clever algorithms that use resources more efficiently, you can start getting good results out of near-term quantum hardware. And that is the challenge of quantum computing in the near term, to design efficient circuits, compact circuits to do very specific tasks. And that's the only way we'll get real benefits out of the near-term hardware. Okay, we're here to learn how quantum computing can help machine learning. But I'll start by saying efficiency has always been a part of machine learning. We use things like reductions to linear regressions. Linear regression, in practice, is a linear time algorithm on sklearn. Neural networks can benefit from accelerated computing, like TPUs, GPUs. And decision trees are incredibly simple algorithms that we can ensemble together in clever ways to make them more powerful. So for quantum computing to go in and change these things and say that we can make them faster as they are would be extremely optimistic. Rather, this focus on efficiency has left some tools on the table that we don't touch because we can't do them today. Those tools are what we think we can unlock with quantum computing. So our approach to quantum machine learning is this. We focus on natural properties of quantum mechanics as they apply to machine learning. These are things like unitary linear algebra, determinants, and high dimensionality, the type of high dimensionality that you saw earlier in the quantum state. And using these tools, we can design custom algorithms for specific purposes. There goes a story about Steve Jobs and Intel. So Apple switched from Power PCs to Intel PCs, or CPUs, in 2005. And that wasn't the first time that Steve Jobs had approached Intel. In fact, Steve Jobs had approached Intel years earlier with a bit of an odd ask. He had seen that Windows PC manufacturers were really tight with Intel, and every time Intel released a new chip, they would grab it up and then market it as the next best thing. But he also saw that Windows did not use the resources as efficiently as possible. In fact, they were dropping up to 40% of the clock cycles. So Steve Jobs went to Intel and said, give me your previous generation chips, and we will build software that uses 90% of the clock cycles. So we'll meet or beat Windows performance with the previous generation chips. The deal did not go through, but he was right. If we design efficient software today, we don't have to wait for faster hardware. And so while the hardware manufacturers are moving from the left to the right, trying to build better qubits and better and faster qubits, we are moving from the right to the left with software that uses fewer resources and can get quantum advantage sooner. When we meet in the middle, that is quantum advantage. But we don't even want to wait that long. So we can actually build quantum-inspired tools that we can run on GPUs today. They won't be as powerful as the quantum algorithms, but they can help us understand if these quantum algorithms will be useful and even get benefits today. OK. If you want to do quantum machine learning, you really have to start from ground zero. The first thing in a machine learning algorithm is getting your data onto the computer in the first place. And we don't even know how to do that. So let me show you a circuit that does that. You can't just plug your flash drive into the quantum computer. It uses a completely different data format. But what you want to do is design a circuit that does this. It loads an n-dimensional vector onto a quantum computer. And you want to do this in a short circuit, too, so you can run it on near-term hardware. This is one circuit that does that. It's the same circuit you saw before. And once you run this circuit on a quantum computer, your data will be in the A's, B's, and C's of that quantum state. OK, that's a great first step. But now we want to build a machine learning algorithm. So machine learning relies often heavily on the dot product. So maybe that can be our second step. The goal is to estimate the dot product between x and y. And here is the circuit to do that. If you look very closely, that first part of the circuit is the same as the data loader. So what we're doing intuitively, the first step in computing the dot product between x and y is to load x. And then the later part of the circuit is actually just the reverse of the data loader. So what you can do is load x, unload y, and at the end you get a dot product. It's beautiful how this math works out. Now that we have the skeleton of a machine learning algorithm, we want to test the feasibility of computers today. Can quantum computers do anything non-trivial for quantum machine learning? So we partnered up with IonQ, who is building trapped ion quantum computers. And we tried running the simplest data set, MNIST, the hello world of machine learning, along with the nearest centroid algorithm, which is one of the simplest machine learning algorithms. And we ran this on one of their state-of-the-art quantum computers. And what we found was we actually got accuracy which was just a few percentage points lower than the classical. This was published in the Nature portfolio journals for quantum information. And to give you context here, it was 3 years prior to this, it was inconceivable that quantum computers could do anything except guess randomly on a machine learning task. So this gives us confidence to continue and design more purposeful circuits with better properties. OK, often we're on calls with people that are learning about quantum computation. And the first 5 minutes are like company introduction, who we are, who we work with. Then they get some time to ask questions. And routinely, the question that we get is, but what can you do about neural networks? There are lots of propositions for how you can help neural networks with quantum computation. And one that we're finding especially promising is to design custom neural network layers that confer special properties from quantum mechanics. And one of those properties is orthogonality. So we're building orthogonal neural networks. Orthogonal neural networks use orthogonal weight matrices. Usually, neural networks have weight matrices. You can put whatever you want in this weight matrix. But in an orthogonal weight matrix, any two columns you choose, they will be orthogonal at right angles. And this gives two properties. One, each column of these weight matrices are now encoding unique disjoint information, which means that you can easily trace the flow. It makes it more interpretable. And second, it has the property of norm preservation. So if you do a regular matrix multiplication, you start with this input vector that's pointing somewhere in space. A normal matrix multiplication can send it to wherever, meaning it can shrink the length as well, or make it longer. An orthogonal matrix multiplication will not change the length of the input vector whatsoever. One of the biggest problems in neural networks is this problem of vanishing gradients. And it makes it very hard to train deep neural networks. A large part of that problem can actually be traced back to the fact that normal matrix multiplication can change the length of the input vector. And this was shown in 2016 by a team of researchers that includes Yoshua Bengio, who is one of the Turing Award winners for pioneering neural networks. The problem is that at this time, it was really difficult to do this classically. Often, the weight matrix would be trained, which would take it out of orthogonality, and then there would be a correction step to bring it back. And that correction step was very costly. Our contribution here was to propose two new algorithms, one of which is an efficient quantum algorithm for doing the forward pass of this neural network, and then a quantum-inspired algorithm to do the backward pass. So now we can train these in n-squared time. And this topic remains at the core of what neural networks are. This paper right here is very recent, 2022, and it includes a researcher, Jan LeCun, who is another Turing Award winner for pioneering pioneering neural networks, just giving more efficient ways to do this. So this is a very important problem in the industry. These are two of the circuits that we use to do this. These both implement orthogonal neural networks, the forward pass. The one on the left is called the pyramid circuit. It's linear in depth, but the benefit is that each 2-qubit gate, each of these vertical lines, only affects qubits that are adjacent to each other, which is very good for near-term quantum computers. And then the one on the right is the butterfly circuit. It's inspired by the fast Fourier transform, and it's just logarithmic depth, meaning it's very, very short. We wanted to try this on real data sets, so we partnered with Roche to run it on some medical image data sets. We used our pyramid networks, and we ran this on an IBM quantum computer. And what we found was that the performance was on par with classical neural networks, except that these had that additional benefit of orthogonality. Okay, there's plenty more work to be done in this field. Recently, we just finished a project with BMW working on quantum convolutional neural networks. We're working with a pharma company on quantum transformer networks. And we're also working with an investment bank on quantum deep reinforcement learning. So lots of work to be done in the field, and lots of industry interest as well. The second algorithm that I want to introduce you to is determinant sampling. This is a way of selecting diverse representatives from a set. If you do a Google search for Jaguar on Google, then if you get the first set of images, you'd be pretty disappointed. That is Jaguars, but it's just cars. And you might not get what you're looking for. The second set of images is better. It's selecting for not only relevance, but also diversity. So for you, diversity is important, but for machine learning as well. If you're training a neural network to detect cats, and you just feed it your cat again and again, it's going to become a your cat detector, not a cat detector. So for machine learning, diversity means generalization. But how do you measure diversity? One way you can do it is featureize your two images, make them into vectors, and then take the area between them. And if the area is small, then they're not so diverse, but if the area is large, then they are diverse. If you generalize to 3 dimensions, if you add another image, then you want to select images with large volume between them. And then if you generalize to higher dimension, it becomes determinant. So the problem of selecting a diverse set is also the problem of selecting a set with high determinant. So we can formalize this a bit. You have an n by d matrix, and you want to select d rows of this matrix. Say this is like users and features. You want to select d users, which maximize the determinant of that subselected matrix, the matrix that only has your selected rows. So we want to select from this distribution, essentially. This algorithm should spit out a selection, and the probability that a selection is spit out should be proportional to the determinant of that subselected matrix. The fastest classical way of doing this is d-cubed time, which is just slow enough that you can't run this on large data sets. If you want to do the same thing on a quantum computer, you need to prepare this state. That's how you write it down mathematically. And our research team has recently showed that you can do this in d-squared gates and d-depth. So d squared is the real comparison between d cubed and d squared. That's the real comparison. D depth just shows us that we can run this on near-term quantum computers because it's not so, the circuits don't build up noise as much. Okay, so this is what the circuit looks like. This is a 5x2 data matrix. We're just selecting determinantal sampling from this. And this is just about the largest we can do on a quantum computer today. Anything more than this, 6x2, 6x3, all of that just results in noise. So if there's any slide that shows you the state of the hardware today, this is it. Okay, what can you do if you can do determinant sampling? Well, say you have a full data set, and it has some missing data, it has some bias to it, and you take a regular uniform sample. The uniform sample will not create a diverse subselection. It will have clumping together, and it will also transfer over any bias that you have in the original data set. Determinant sampling, on the other hand, will try its mathematical best to cancel out the bias in the original data set, to span the entire space, and you won't get clumping. And when you can do this, you have some very powerful applications in machine learning. First of all, you get a lot of unbiased estimators from Monte Carlo. You can prevent mode collapse in generative networks. And you can also reduce variance in ensemble methods. This last one we wanted to check out, so we partnered up with Itaú, which is a large South American bank. They had a case that was trying to predict how likely somebody is to leave their bank. And internally, they were using a random forest model. So we worked with their team to enhance the random forest model with this determinantal sampling. And we ran this on an IBM quantum computer. Now, you saw we could not run large parts of this data set on the IBM quantum computer. But we did do some tests, and we saw that, in fact, the variance was reduced for every tree that we trained on from a determinant sample. But of course, we wanted to run their whole data set. We wanted to actually solve their problem. So we devised a variant of this algorithm that could be run just on GPUs. It didn't have the full power of quantum algorithms, but it did allow us to run the full data set. And when we did this, we found a 7% improvement in precision on top of their model that they were already using in production. So this is quantum-inspired ROI. Okay, the third algorithm is topological data analysis. It's an algorithm that's gaining a lot of popularity in machine learning, but it's hitting some very profound barriers. And that's because most of this computation cannot be done on a classical computer. And we hope that quantum computing can unlock this. There goes a story that I used to hear as a kid. It comes from Asian cultures. There was a village, and in this village, there were a few blind children. And one day in that village, an elephant came to town. The kids wanted to understand what an elephant was, but they didn't even know it was an animal. So they were placed around the elephant and then asked to give their opinion about what an elephant was. One of them, that was placed at the very base of the foot, said, "This is like a big tree." The one that was at the tail said, "What are you talking about? This is a rope. They're tricking us." And then the one that was placed at the tusk said, "Guys, this could kill us all." So the moral of this story is that the big picture matters. And so it goes with your data. Often we use algorithms that are looking at pairwise distances. And in general, looking at distances is the geometry of your data. Topological data analysis implores us to go beyond the geometry and start looking at the topology of our data, which is the shape. Now, we do this already with clustering. And clusters are one kind of useful shape. But topology teaches us that there are more kinds of useful shapes, like loops, voids. In general, these represent higher order interactions between your data, like feedback loops or internal structure. And these kinds of higher order interactions show up all the time. For example, in your brain, where there are many parts of your brain collaborating for a single purpose, or in the financial markets, where trends influence trends, influence trends. These things show up all the time in nature. And these kinds of global properties of data seem to be exactly the kind of things that quantum computing is good for. So this is quite promising. You see an 8 here, right? A computer does not. So how do you get the computer to understand that this is an 8? One thing you could do is cluster it, but you'd probably lose much of the beautiful structure of this data. I mean, there's 2 massive holes in it. You could also run some visual recognition algorithm, but that only works in 2 dimensions and 3 dimensions. Your data set could be thousands of dimensions. One algorithm to do this is called persistent homology. The idea is to start with a little ball of radius 0 around every single data point. And then you grow this radius from 0 all the way to, say, 100. At r equals 10, you start getting a little bit of overlap. And every time you get an overlap, you link those 2 points together. At r equals 10, you don't get too much structure. You're not really looking at the structure of this data. But at r equals 50, you start seeing the real structure of this data. There are clearly 2 massive holes. And then at r equals 100, some of these holes start getting filled in. So the top one did not survive, but the bottom one survived. This is another piece of information that you can get about your data, about the holes, is how long do they survive. That tells you how important they are and how big they are. Okay, this calculation is extremely hard. For just these 3 points, you need to calculate the rank of this gigantic matrix. And in general, this matrix is called the boundary matrix. It's exponential in size. So even to represent this on a regular computer, classical computer, is very difficult. It just so happens that this operator, this boundary matrix, if you modify it in a small way, you can fit this naturally onto a quantum computer. It becomes a natural quantum operation. But more on this later. The regular computation of this persistent homology algorithm goes back to 2005, and a little bit before this as well. But the issue is, even though you can speed this computation up with GPUs, it's just absolutely infeasible for larger dimensions. So you can calculate clusters, you can calculate loops, you can calculate voids, which are like the inside of the balloon, but you can't calculate more than that. It's very difficult to do that, and that's because it's an exponential time calculation on a classical computer. Then in 2015, it was introduced that we can get an exponential speedup on a quantum computer on this calculation. But 2 notes here. One, it's with additive error. So it can tell you that your data set has 200 holes, but plus or minus 5. So we don't know how bad that additive error is, and if it stops us from using this algorithm in the same ways that we would have. And then the second caveat is that this circuit is incredibly deep, so we can't run this on near-term devices. Our contribution from our research team in 2022 was that we can actually encode this gigantic boundary operator in just logarithmic depth on a quantum computer. And this, alongside some other very promising work in quantum topological data analysis, allows us to start experimenting with this in the next few years. So this is a huge leap. And even though you can't do those higher dimensional calculations, just with the clusters, loops, voids, you can start doing some very interesting things in a lot of different fields. I talked about computational neurobiology, where these topological data analysis can naturally model these interactions between the brain regions. Also, neural networks, if you enhance neural networks with topological features, they can be very, very powerful. There's a competition in molecular biology called the D3R challenge. And lots of teams are competing to predict properties of proteins. And one team started to use neural networks enhanced with topological features. And they won almost every single competition that they participated in for 2 competitions in a row, the 2 most recent ones. So very powerful neural networks. For time series analysis as well, for anomaly detection and even things like predicting market crashes, topological data analysis has been proposed, and there have been some very promising results. So lots of power here, and we hope that going to further dimensions just increases this power, but we won't know until we try. Okay, last algorithm. This one is especially representative of what quantum algorithms will probably look like. And that's because there is no research on this. There's limited research on this. The literature is very sparse because this is an exponential size matrix, and we can't compute this on a regular computer. So this is what it looks like. If you have this A matrix here, which may represent pairwise interactions, the compound matrix is an exponential size matrix, of course. Well, exponential when C gets large, when the the order of the compound matrix gets large. And it's the matrix of determinants. So this is the second compound matrix, which means it's the matrix of 2 by 2 determinants that you can grab from A. So you can see the first determinant is 1, 2, 5, 6. The second is 1, 3, 5, 7. As you can see, the second element in the compound matrix. If you go further and you change the row, that changes the row in the compound matrix, and the pattern continues. So this is a very large matrix, and it was first introduced in the context of ordinary differential equations. Then in 2005, it was shown that it is the backbone of these Binet-Cauchy kernels for machine learning, which generalizes a lot of the kernels that we use today in machine learning. And our contribution here is that we can do efficient operations on these compound matrices, like the singular value decomposition on a quantum computer. And hopefully this will bring the compound matrix into the repertoire of a machine learning workflow. All right, so now for some takeaways. These powerful but unexplored algorithms are being found everywhere. They have their backbone in quantum mechanics. And some of them force us to think in different ways than we would have, to force us to think outside the realm of classical efficiency. It also takes many years to design these algorithms and get them ready for production. The research for these typically involves understanding some deep connection between the linear algebra that's used in your use case and the linear algebra that's used in quantum mechanics. And this can take years. And also productionizing these algorithms, as we see from machine learning, can also take a long time. We saw algorithms for neural networks, for determinant sampling. These two actually have quantum-inspired applications that you can use today on medium-sized data sets. So these are things that you can use today. Topological data analysis and compound matrices, these are things that you can start experimenting with. These are both fundamental shifts on how we think about problems, going from pairwise interactions to larger order interactions. So these we can start thinking about today and understanding if they're good for our use cases. I think that near-term quantum machine learning is not about waiting. It's about sticking a quantum mechanics person, a computer scientist, and a data scientist. You put them all in a room, and then you see what kind of beautiful ideas come out. Thank you. All right, I can take questions now. Question?
In the presentation, I noticed a lot of two-dimensional representations. Is that just for limitations of being able to?
Yeah, absolutely. Yeah, so the question was, in the presentation, there are a lot of 2D representations. That is just because I can show 2D. Of course, all of these algorithms work for higher dimensional data sets as well. Question in the back? It's not a coincidence. The math works out that way, but it's not a coincidence. The question was, is it a coincidence that loading the array and then unloading the array creates the dot product? I would say it's not a coincidence. There's some structure in the dot product that shows up in these in quantum mechanics as well, in this kind of linear algebra. It is beautiful. Yes?
Are you able to comment on the stability of these qubits as you go from 100 to 1,000?
So in general, qubits today are not stable. So the question was, can you comment on the stability of these qubits as you go from 100 to 1,000? And lots of different architectures act in different ways. I'm not a hardware person, so I probably can't comment on this in particular. But these qubits are generally not so stable. They have very, very short lives. So if you load your data into a quantum state, you really have to complete your computation very quickly. And that's an issue, but not so much in the experimental stages. Yes?
Could you define very quickly, like
Oh, it's like milliseconds, nanoseconds, yeah.
When you were talking previously about the margin of error, so you calculate something to large scale but with plus or minus 5, do you find in different systems that that plus or minus value for the same calculation is always similar, or do you find it decaying over time or things like that?
Sorry, can you repeat the question?
You were talking earlier about deterministic modeling and how you can calculate in a standard computer, a smaller set with a degree of accuracy, but a quantum you can do a larger set with variable accuracy. Do you find that that variable amount is consistent through different types of quantum computers, or does it tend to be variable based off of each calculation?
So are you asking, between quantum computers, do those error bars change?
Multiple runs. Do you find
Oh,
that
yeah.
variability, like if you run the same algorithm 5 times on the same quantum computer,
Yes.
does that variability change, or is it always consistently a margin of error?
Okay, so the question is, when you do one of these runs and you expect a probabilistic outcome with some error bars, do those error bars change every time you run the calculation? And the answer is, the statistics of the error bars don't change. But you'll get different results, of course. But yeah, the statistics of the error bars do not change whatsoever. Yeah, you can lock that down. If you lock down your data set and you lock down the algorithm, yeah, you can calculate that.
You mentioned like to scale it up to like medium-sized problem, use quantum-inspired algorithms. Like how do you implement those specifically? Like what does that mean from an implementation?
Yeah, so there are various different algorithms to do classical computations. And some of these quantum-inspired algorithms are just, we did it on a quantum computer. We found an algorithm on a quantum computer. How much of this can we do on a classical computer, right? And sometimes it's just running this on a simulator. We've actually found that some algorithms we can match like the cutting-edge classical implementations with simulations of a quantum computer, which is very promising. Other algorithms, like for example, the neural networks algorithm, it's inspired by a quantum algorithm, but we can kind of like do the linear algebra with some shortcuts on a classical computer. So the answer to that question is we design these classical algorithms that are just inspired by the quantum mechanics. So it's just like any regular machine learning algorithm. Yeah. They have nothing to do with quantum, if that's what you're asking. Yeah, you can do this completely on a GPU or a CPU. Yes, of course, yeah. These quantum-inspired algorithms tend to fit naturally onto GPUs. Because of this, they can do parallel computation, and that's kind of how you would simulate a quantum computer as well.
Are you doing your development natively at the circuit level, or do you use frameworks like PennyLane or Quantum TensorFlow, or is it a mix of all those things?
Yeah, the question is, do we use frameworks for the development of these circuits? We do it at the circuit level. We just go, yeah. There's no frameworks for it because these circuits need to be very, very compact and efficient. Of course, we're building frameworks ourselves for building up these things, but they tend to be very, very specific functionality. Right now, we're not at the software stage because intrinsically, if you build software, there's going to be inefficiencies with that level of abstraction. So we can't do that right now. But we think it's very promising, yeah, in the medium term. Yes?
What was the name of the paper for efficient SVD that you cited for compound matrices?
It's called machine learning with subspace states, quantum machine learning with subspace states. Yeah. All right, if no more questions, thank you so much. We'll be around, me, Steve, Matthew's here, for any questions. Thank you.